Welcome back. Having completed the module on energetics, we will move on to a new module. This will involve a series of lectures on different aspects of nuclear kinetics. In this first lecture, in this module, we will just introduce the nomenclature, which we've already done in the past, but in slightly more detailed manner. So we will look at the different kinds of radioactive decay. But before we get started, it's important to understand that even when we are talking about kinetics, energetics is quite important. When you discuss the criteria for radioactive decay, the criteria is based on energy. So that the parent is less stable than the products of the reaction is very important. So the difference between the masses of the reactants referred to as the product parent and the products are the masses are indicative of energies. So the difference between them, this is higher energy state, this is a lower energy state, the difference in masses um, are can be correlated to differences in energies, that is being referred to as Q. This has to be greater than 0. So the take home message is that the driving force for kinetics is based on energies. So there can be different pathways depending upon the activation barriers along different modes to get from the parents to the products. So these different activation barriers along the different pathways will determine the rates of change along the different pathways. So these are the different mechanisms that are possible to take you from the products to from the reactants to the products. So the most common radioactive decay you might have heard is the alpha decay. So this is a common way to uh, document an alpha decay. So what is important to realize here is when an alpha particle is ejected, the atomic number decreases by 2, atomic weight decreases by 4, and these are conserved, right? So if you, because the alpha particles have 2 protons, that's why we have this balance in atomic number. It has 4 nucleons, that's why we have this balance in atomic weight. Perhaps the most common alpha decay reaction which you might have seen is this uranium getting converted to thoria with this atomic number and atomic weight uh, along the alpha decay pathway. Beta decay is not one single thing, uh, but this is the form of beta decay you might have uh, seen in the past. So these are electrons which can be proved by a set of experiments. When you say beta decay, it is just that you are ejecting an electron. Um, so what happens? So the atomic number increases, atomic weight does not change. And then we have this one new object, which is an anti-neutrino. We won't talk about this a lot, but this has to be introduced. This was introduced theoretically by Pauli, and it was later experimentally documented in, I think, 1956. So there are 2 other forms of beta decay. So there can be a beta plus decay, wherein a positron is emitted along with a neutrino. Neutrino and anti-neutrino have neutral charge uh, like a neutron, but they have very different mass compared to that of a neutron. So in a positron emission, the atomic number decreases, but the atomic weight does not change. And then you have something called electron capture, which is also a beta decay. So all these things are categorized within the same beta decay uh, mechanism, because there is commonality in the mechanism, operational mechanism for all three processes. We will perhaps take up this bit later in this module. So in electron capture, what happens is that an electron outside the nucleus is captured and it combines with a proton. Therefore, your atomic number decreases, but atomic weight does not change, and then there is a release of a neutrino. So all these three are categorized under beta decay. Then you have an alpha decay, wherein there is no change in atomic number or change in atomic weight, but a high energy state, it can be a metastable state that has been arrived at via radioactive decay trajectory, or it has been excited in some manner. So when this excited state gets de-excited, it emits a gamma photon. So along with this de-excitation, there is also a change in structure, because energetics is always correlated to structure. So the nuclear or the nucleon configuration in this excited state is different from the nuclear and the nucleon configuration in this ground state. Gradually, we will build some intuition what are the different nucleon structures that are possible in excited states. We have already seen some kind of an excitation, for example, under the liquid drop model, when the nucleus goes from a spherical shape to a non-spherical shape, there is an increase in surface energy and there might be a decrease in Coulomb energy. That is one kind of an excited state. So we will look at different configuration that it can be connected to excited states later in this course. So another form of nuclear reaction is the spontaneous fission. Here, a large molecule, nucleus, in this case, californium, breaks down into two smaller nucleus, denoted here as F1 and F2, along with the emission of 3 neutrons. In the next lecture, we will look at the ways we can document the kinetics, that is the rate of change in along these different nuclear pathways. That's going to be the topic that will be taken up in the next lecture. Thank you.